The 2x2 determinant, I want to derive this formula using the area properties that we came up with from the last video. So we said if A is the matrix with columns AC and BD, then the determinant of A is the area formed by the parallelogram made by these column vectors. The area of the parallelogram formed by these column vectors, I should say. And there's a way to derive this the formula for the 2x2 determinant using, if we write the first column as AC and the second column as BD, and we actually make the parallelogram. It's not very parallel. I'm not sure that is either, but okay. It's possible to think about, you can sort of draw a picture. It turns out, this point right here actually is A plus B comma C plus D, if you want to think about it that way, or the vector A plus B comma C plus D. And you can draw this little bounding box. You can draw the box here, and that has a certain area, and then you can break all this up into, there's these triangles and square and rectangles and stuff. And you can sort of take the entire rectangle and subtract off, this and this and this and this and this and this. And you can show that the area of this is AD minus BC. You can actually show that. So, but I want to do it a slightly different way. I want to use it using the, I claim I can actually derive the formula using these area properties. By all means, you should definitely pause the video and go through the argument to show that if you draw this parallelogram, draw the bounding box and subtract off all the pieces, that you do get AD minus BC. But I want to derive it a slightly different way. And remember, I just want to use a couple of the properties we talked about. So the first property we talked about was that if we have vectors, something like this, that, the area formed by V1 plus V2 and V3, then that's the same thing as the area formed by V1 and V3 plus the area formed by V2 and V3 that's one of the properties. And then the other property is that if we have a zero column, the area formed by 0 in V is just 0, right? I would just want to use those two. So, and then another thing I want to, okay, there's a notational thing I should mention, which is that if A is the matrix ABCD, then determinant A is often written, it's going to look very similar, but it's more like an absolute value sign. Here we had their little brackets. And sometimes people write, use brackets or parentheses to write a matrix. But over here, when you write the determinant, if you sometimes just put little like absolute value signs instead. So if I write that, I actually mean the area, not actually the matrix. So it's kind of a weird thing, but because it still looks like a 2x2 array, but those vertical bars mean we're going to write down the, that means the determinant. Okay. So if we apply these properties, I want to start with, so if we start with A, B, C, A, the determinant, and I want to think about something here. I want to think about the fact that we could rewrite AC as A0 plus 0C. A0 plus 0C. Okay, and I want to think of that as being like the V1 plus V2. Up there, up above in that area formula. And so what that says is that actually says that, it's kind of strange, but it says that I could write something like, if I translate the area property above and say, well, it breaks up, the vector breaks up into two vectors, then the determinant also breaks up. Oh, that's a B right there, sorry. Like that, right? Oops, I wrote a square bracket, but I'm gonna absolute value sign. Okay, so that is, it's kind of weird, but that's true, because if we think of, I'm basically thinking, I'm using the property up here. I'm using this property. And so this is V1 is A0, V2 is 0C, and V3 is BD. And this is true. But then if I do the same thing, I break it up and I think of B comma D as B0 plus 0D, I can actually break these up further. So I could think of this as A0, B0 plus A0, 0D plus 0C, B0 plus 0C, 0D. And now what? Well, this is sort of interesting because these two have a 0, 0 row, have a 0 row. And we said rows and columns are interchangeable when you think about determinants. So 0 row is just like having a 0 column. We said that makes the determinant, the area is 0. So this equals 0. This equals 0. And now we're looking at the area formed by A0 and 0D. Well, that's sort of clearly, if that's A0 and this is 0D, then the rectangle formed by them clearly has area AD. So this equals AD. And if we think about the rectangle formed by 0C and D0, we can think about this one of two possible ways. We can either think of the property we showed, which is that if we switch two columns, we pick up a minus sign, or we can think that here's 0C, here's B0, and we can think of the fact that the area is a signed area, right? And here, in this example, we were going counterclockwise from A0 to 0D. Here, because 0C is first, we'd be going clockwise from 0C to B0. And so this area is actually considered to be minus BC. So you could write that, yeah, so then this ends up being negative BC. And so at the end of the day, we get that the total determinant is just AD plus negative BC. And so just using those properties, we've derived the original formula that we had seen before. So it's kind of nice that it falls out this way. And in the next video, I'll talk about how it falls out for the 3x3 determinant. It's a little bit more complicated, but we can use some more volume considerations and get at least see how a formula works for 3x3. Okay.